All right, let's get right into it. Every time you stream a video, fire off an email, or just load up a web page, you're relying on a massive, highly coordinated system that's working flawlessly in the background. It's kind of like magic, but today we're pulling back the curtain on the actual network software and standardization that makes global digital communication possible. So think about this massive problem for a second. How exactly does your smartphone seamlessly talk to a server halfway across the globe? I mean, you've got devices made by Apple, Samsung, Cisco, and countless others. They use totally different hardware, entirely different operating systems, and different local networks. Yet they connect instantly. How on earth do they avoid complete digital chaos? Well, to make sense of it all, we're going to logically trace the journey of your data. We'll look at network standards, unpack the OSI model, check out multiplexing, dive into switching, and wrap it all up with TCP to see how reliable delivery is guaranteed. Starting off with Section 1. Why networks actually need standards. This is the absolute foundation. Here's the deal. Without these agreed-upon rules, the internet as we know it literally wouldn't exist. Imagine if a tech company just decided to ignore the standards and build their own proprietary communication rules. Sure, they could do it, but their networking products would be entirely unmarketable because they wouldn't be able to connect to the wider world. It'd be like inventing this revolutionary, ultra-fast high-speed train, but laying tracks that don't fit any other railway on the planet. Standardization actually fosters innovation because it gives everyone a common, reliable foundation to build upon. Which brings us to Section 2. Let's unpack the OSI model. Now, this is where it gets really fascinating. The Open Systems Interconnection model breaks down all network communication into 7 functionally independent layers. At the very top, you have the application layer. That's where your web browsers and email clients live. Then as we move down through presentation and session, your data is translated, encrypted, and synchronized. Keep going down to transport and network, and your data gets broken into segments and packets for routing. Finally, at the very bottom, we hit the data link and physical layers, where your data is actually converted into raw bits, just ones and zeros, ready to be shot across a physical wire or a radio wave. This is such a brilliant way to look at the division of labor. We essentially have 2 distinct teams working here. The upper layers are all about you, the user. They translate, encrypt, and manage the host messages so the software actually understands what's going on. The lower layers? They don't care at all about what your message actually says. Their job is strictly the heavy lifting: physical routing, addressing, error checking, and blasting that hardware transmission across the globe. Moving right along to Section 3, multiplexing, or how we share the line. Okay, so once our data hits that bottom physical layer, we run into a very practical problem. We can't possibly run a dedicated physical wire for every single device on Earth. It's just not going to happen. Enter multiplexing. Think of it exactly like a massive highway system. A multiplexer acts like a multi-lane on-ramp, taking multiple distinct data streams and merging them into one incredibly fast lane. Then, at the other end of the line, the demultiplexer acts as the exit ramp. It takes that combined high-speed signal and carefully splits it back up into its original separate components so they go to the right receivers. So how do we mix all these signals without them just turning into a jumbled mess? Well, depending on your network medium, you've got a few options. Frequency division multiplexing separates analog signals by assigning them different frequency bands, kind of like different radio stations. Wavelength division multiplexing does the same thing, but it uses different wavelengths of high-frequency light, zooming down fiber optic cables, which can carry literally terabits of data per second. And then there's time division multiplexing, which is digital. Instead of splitting frequencies, it gives each signal a strict, rotating time slot to use the full bandwidth of the line. You can see here just how incredibly efficient this makes our networks. Squeezing multiple user signals over one shared wire saves absolute mountains of physical bandwidth and infrastructure costs. Whether we're talking about your local telephone network or those massive fiber optic backbones crossing the bottom of the ocean, multiplexing really is the silent hero here. All right, Section 4, let's talk about switching and routing the via. Over the years, we've had to figure out the best way to route all this data through a maze of network nodes. Old-school telephone systems used circuit switching, which created a dedicated, locked-in physical path between 2 people. The problem? If you weren't talking, that line's bandwidth was just completely wasted. Then we had message switching, where an entire message is stored at a node and forwarded when a line frees up. But today, the internet relies almost entirely on packet switching. This brilliant method slices your data into small, manageable, independent blocks called packets. Because they're small, they can be dynamically routed over tons of different lines at once.
It allows for incredibly high efficiency and a much fairer sharing of network resources.
And finally, Section 5, TCP, ensuring reliable delivery. So we've sliced your data up into packets and we've fired them off across multiplexed lines through all sorts of network switches. But how do we guarantee that those scattered, dynamic packets actually arrive perfectly at their destination? That is where TCP, or the Transmission Control Protocol, steps in. Sitting securely at the transport layer, TCP is basically the ultimate shipping manager for your data stream. TCP does not mess around. It is rigorous, and it works incredibly fast. First, it's connection-oriented, meaning it formally shakes hands and establishes a connection before it sends a single byte. It provides a rock-solid connection by attaching checksums to verify data integrity. It tracks byte sequence numbers, so if packets arrive totally out of order, it perfectly reassembles them. If a packet gets lost in transit, no problem. TCP demands an automatic retransmission. It even monitors network congestion to slow things down if the network is getting overwhelmed. It ensures absolutely nothing gets missed. So what's the big takeaway here? Your entire daily digital life is only possible thanks to this beautifully structured, highly standardized journey of data. From the application layer all the way down to physical pulses of light in a fiber optic cable, these rules ensure that your devices can seamlessly talk, share, and connect, all without you ever having to worry about the crazy chaos happening beneath the surface. But here's a question to leave you with. As we push for higher and higher bandwidths, lower latency, and connect literally billions more devices globally, the strain on these foundational models is only going to grow. If protocols like TCP guarantee every byte arrives perfectly today, how on earth are these models going to evolve to handle the massive, instantaneous speeds of tomorrow? It's something to think about. Thanks so much for joining me on this explainer, and I hope you look at your internet connection with a whole new level of appreciation.